Good morning. In today's session, I want to talk about this topic on the creation or generation of what we call standard reduction potentials. So, as we saw in the last one, or mentioned anyway, that we have what are called standard cell potentials for our voltaic cells. And these depend on the materials that are involved, right? It depends on what half reactions are involved, right? Are we looking at the oxidation of zinc or the oxidation of iron or whatever it might be, right? So the magnitude of this standard cell potential depends on what materials are involved. So one way that we can approach this is that we can think of each half reaction as having its own what's called standard electrode potential. Right? So we have standard cell potential, right, which is for an electrochemical cell, and each half of that cell would have a standard electrode potential. Now, unfortunately, of course, we can't measure the absolute potential of a half reaction directly, right? We have to have the process. There has to be some sort of redox process involved in order to measure what this is. So what we can do, though, is we can measure it relative to another half reaction. Well, how is this going to be useful to us? Well, if we were to take all sorts of half reactions and measure them against the same half reaction, then we could develop a relative table of standard electrode potentials. And that's exactly what they did, right? They took what is called the standard hydrogen electrode, or the She electrode, and that became the standard which against all other cells or all other half reactions were measured against. And so essentially they took all of these other ones and paired them up with the She electrode, and they looked at what happened. So they selected a standard half reaction, which is the She electrode, and this involves the reduction of hydrogen ions to hydrogen gas, right? So electron is undergoing a 2-electron reduction here. And this was arbitrarily assigned a standard electrode potential of 0. Right? So we give this, and so if you were to hook this up with itself, in other words, so you had the same electrode on both sides, right? You would see zeroed potential. In other words, nothing would happen, right? Because it's the same on both sides. So this becomes our 0 point, right? And we're going to put this half reaction up against all of the other half reactions that we might want to study. And we're going to look at the relative potential. We're going to look at what the cell potential is, right? Do we generate a current or a voltage, right? Spontaneously or not? So, a couple of key things, right? So I said the She reduction potential is assigned 0. Now, you'll notice we will start to think about everything as a reduction potential. Even though in a particular cell it may not undergo reduction, the standard potentials, electrode potentials, we're always going to think about those as reduction potentials, at least to begin with. So standard reduction potentials compare the tendency of a particular half reaction to occur relative to the reduction of hydrogen ions to H+, of course, under standard conditions. So, in other words, is the half cell that we're looking at have a higher potential to undergo reduction than the She, or a lower potential to undergo reduction in the She? And so half reactions that have a stronger tendency to undergo reduction, what we're going to see is they're going to undergo the reduction, and the She will actually undergo the oxidation. So in other words, hydrogen will be converted into H+ ions. And so that'll be given a positive value for the electrode reduction potential, right? Meaning it has a stronger tendency to undergo reduction compared to the She electrode. So it's given a positive reduction potential or standard reduction potential. So half reactions with a stronger tendency toward oxidation, or in other words, a lower tendency to undergo reduction than the She electrodes, what we're going to see happen is it's going to undergo, the half reaction that we're studying is going to undergo oxidation, and the She will undergo reduction, and these will said be have a negative reduction potential compared to the standard hydrogen electrode, or it's less likely to undergo reduction if you want to think about it that way, right? And so now we're going to have the series, right, where we have the She with the 0, and then we have some half cells that have a higher tendency to undergo reduction, so they would rather undergo reduction than the She. Those are going to have positive potentials, and then we have ones that are less likely to undergo reduction when hooked up to the She compared to the She electrode, and they're going to have negative reduction potentials. And now that we have this whole series, we can start to pick and choose things from this series, right? And if we pair, we're always going to see electrons flow from the more negative reduction potential to the more positive reduction potential. So one way to think about it is that things at the top of the table really want to gain electrons, right? Things lower on the table really want to have a higher tendency to want to lose electrons. So electrons are always going to flow sort of up the table, if you will, right? So electrons are going to flow from whatever has the more negative to whatever has the more positive reduction potential. Now, we use the term positive and negative, but it's important to remember these could both have positive potentials, right? They're going to flow from the one that is the lower, that might be negative or it might just be small positive, to one that has a more positive reduction potential. Now, if we were to want to write something or quote something as an oxidation potential, then it's important to understand that the oxidation potential is simply the negative of the reduction potential, right? So it's the same process, just backwards. So we're just going to flip the sign. So if it has a certain reduction potential, then its oxidation potential would be the same number, but positive instead of negative. So let's look at an example here. So let's say we took our zinc electrode and hooked it up, compared it to the She electrode. What we would observe, right, is that the zinc, right, is going to have a more negative potential compared to the She. So what does that mean, right? So if we look back, right, electron flow, half reactions that have a stronger tendency toward oxidation or a weaker tendency toward reduction compared to She are going to have a negative value for the reduction potential. So what this is telling me is that when you put these two together, right, zinc is going to prefer to be oxidized in the presence of the She, so it's going to undergo oxidation, and the She is going to undergo its reduction. And that's what we see, right? We put these together, we see the oxidation of the zinc, and we see the reduction at the She. So since that's what occurs, that means the zinc has a lower tendency to undergo reduction compared to the She electrode, and therefore would be assigned a negative potential. And what's going to be the magnitude of that? Well, what is the potential in this cell? It's 0.76 volts. So that means the reduction potential of the zinc is going to be equal to this back, going to be equal to negative 0.76 volts, right? Negative because it has a lower tendency toward reduction, and 0.76 volts because that is the amount of voltage, the amount of potential difference we see between these two cells. So that's how all of these reduction potentials were generated. Now, another way to think about this, right, is to look at our cell potential, right? So we had our cell that we hooked up. So we have there's a high tendency toward, has a large positive half cell potential. So that's going to, when two half cells are connected, the electrons will flow so that the half reaction with the stronger tendency will occur, right? So, in this case, right, the anode, right, the zinc had a higher tendency toward oxidation. And so, it had the negative 7.6. The cathode, the She, right, that's a 0 voltage, right? But what we saw was, we saw reduction of the She and oxidation of the zinc. So that means that the zinc had a more negative reduction potential, and the absolute value there was 0.76. And the way that we could calculate the cell potential, right, is to simply take the reduction potential at the cathode, right, minus the reduction potential at the anode. So we saw in the voltmeter that our cell potential was 0.76 volts. We know that where the reduction took place at the She has 0 volts. So if we solve for the anode potential, right, for the reduction potential at our anode, we solve for a negative 0.76 volts, right? This is the reduction potential of our zinc, right? Negative 0.76. So by looking at what we measure as our cell potential on our meter, and knowing that the She is 0, right, and we saw what happened, we saw that the zinc underwent oxidation, we can come up with this 0.76 volts, right? Because it's always cathode minus anode is how we calculate the cell potential. All right, so we just saw that zinc has a negative cell potential compared to the She electrodes. So, in other words, electrons will spontaneously flow from the zinc to the She electrode, allowing the She electrode to undergo reduction, the zinc to undergo oxidation. Now, let's say we did the same thing and we hooked our She electrode up to our copper electrode. What we see is that we read a cell potential, right, in our meter, right, of negative 0.34 volts. So what that's telling me is that there is no potential, right, for electron flow between copper as an anode, right, and the She as a cathode, right? It's a negative cell potential, meaning it's actually disfavored by 0.34 volts, right? So it's non-spontaneous. That will not occur. What would occur, right, is the opposite, right? There would be a positive 0.34 potential for the She electrode to undergo oxidation and the copper to undergo reduction. So copper has a stronger tendency to undergo reduction as compared to the She, and so as we said earlier, it will be assigned a positive reduction potential compared to our She electrode of 0. And so by combining these two, we now see that our zinc half reaction has a negative 0.76 reduction potential. Our copper half reaction has a 0.34 reduction potential. Notice these are all reductions. And this, because this is how we're going to use our table. And so zinc does not undergo reduction, right? Copper does. So when we think about the cell and we put this together, we have a zinc that has a high tendency not to undergo reduction, but would like to undergo oxidation. Right? So remember, it's going to be lower in our chart, right? If we think about positive numbers at the top and negative numbers at the bottom, and remember, electrons are going to flow from the more negative potential, right, to the more positive potential, right? So electrons are going to want to flow like this. Okay? So how do we then figure out what's going to be the voltage if we set up this cell? Well, before we do that, let's look at our table. So, as I said, this can be used, we set everything up against the She electrode. Notice the She electrode down here. Right, is 0. Everything above this has a higher tendency to undergo reduction than the She. Right? So we find our copper right here. So copper was 0.34 volts more likely than the She electrode, or to undergo reduction than the She electrode. And you can see lots of other materials, that are more likely to undergo reduction, right? So we have copper ions. You look at things that are, more likely to undergo reduction here. If you then look lower in the table, okay, you see things that are less likely to undergo reduction, or in other words, would more likely want to undergo oxidation if paired with the She electrode. And if you look at our zinc down here, our negative 0.76 reduction potential, and this is where you're going to find the bulk of metal ions, right? Most of these metal ions will really want to undergo oxidation, and so they have these negative reduction potentials, right? The metals that really are really stable and don't want to undergo oxidation are things we're going to find up here, like silver and gold and copper, right? Things that are less susceptible to oxidation, more likely to undergo reduction. So this is where we're going to get our numbers, right? This is where we're going to get what we've referred to as our standard electrode potentials. And again, these are always reduction potentials in our table. So how do we calculate these, though? So there's two basic ways we think about calculating these. To get our cell potential, we can think about it as the reduction, and these are using the reduction potentials. So we can calculate the reduction potential of the reduction minus the oxidation. Or we can think of it as the cathode minus the anode, right? So this is using the electrode where the process occurs. This is using the process itself. So it is reduction minus oxidation, or cathode minus anode. So when we go to calculate these, we do not multiply by coefficients. That's the first thing, right? So in thermodynamics, we get used to a lot multiplying by coefficients because thermodynamic values are extensive. cell potentials are not extensive, right? It doesn't matter how much of the material you have, you'll generate the same potential. So you could have a small sample of zinc or a big sample of zinc. It's not going to change the potential. So we use the value as given no matter how much that we have, right, in our balanced equation. If it's higher in the table, right, more likely to undergo reduction. Lower in the table, more likely to undergo oxidation. Okay, so let's just close out this little section here by using this formula to figure out what would be the cell potential for this zinc copper cell that we have. So if we take the reduction potential of our cathode, remember that's the copper, right? So that's a positive 0.34 volts in our table, and minus the reduction potential of our anode, so that's a negative 0.76. So we get positive 0.34 minus a minus 0.76, or plus a positive, we end up with positive 1.1 volts as what would be our sort of theoretical maximum potential that we could generate with this cell. So if everything worked perfectly, we hooked up our voltmeter, we would generate 1.1 volt potential difference between these two half cells here. So we can use this to calculate the cell potential of any pairing, right? And that could allow us to know whether it's going to be spontaneous, meaning a positive potential, or negative, which would indicate something that would not occur as listed, right? That would be a non-spontaneous reaction. So we can just think about predicting spontaneity by looking at the values in the table, right? So remember, things at the top are likely to undergo reduction. They're going to be good oxidizing agents, right? They're going to cause other things to be oxidized. So if you're looking at a half cell or a reduction potential at the top and you want it to undergo reduction, you want to pair it with anything below it to undergo the oxidation, right? So that means below it, you're going to get the reverse reaction or the oxidation reaction. Where substances near the bottom of the table will undergo oxidation, they're going to be good reducing reagents. So you want to pair a good oxidizing agent with a good reducing agent to get a spontaneous process. So you want to pair a reduction with the reaction below it to undergo the oxidation. So one other way to think about it is any reduction reaction in table 23.1 is spontaneous when it's paired with the reverse or the oxidation of any of the reactions listed below it on the table. So we saw copper, reduction of positive 0.34 volts, so we could compare that with any reaction below it and it would undergo the reverse reaction. Zinc is one of those, but what you can see is that copper paired with almost any of those metals, right? Almost any other metal, the copper is going to undergo reduction, or the copper ions are going to undergo reduction, and that metal is going to undergo oxidation to give us our redox reaction. So this would be our reaction that would occur, right? Zinc undergoing oxidation, copper undergoing reduction. Now, we saw earlier that I put a piece of zinc in our copper and I got this nice reaction. Right? But you can also see that if you take a piece of copper and you put it in a solution of zinc ion, nothing will happen, right? Non-spontaneous, because what you're asking copper to give up its electrons to undergo oxidation in the presence of zinc ions, right? That wouldn't happen, right? If you tried to do that, if we calculated the E cell of this, right, and you got your E of your cathode, right? No, in this case, your zinc is your cathode. So minus 0.76 volts minus 0.34 volts. So you get minus plus a minus, you get, you get a cell potential of minus 1.1 volt, right? Or in other words, this is non-spontaneous by 1.1 volts, right? Not surprising, right? It's the same voltage that we saw in our spontaneous, right? 1.1 volts. Same voltage, but negative, right? Non-spontaneous, because these redox reactions only occur spontaneously in one direction. Now, another sort of useful thing that you can do with this is this reduction potential table will allow us to predict metals and acid and how they react, right? So if we think of metals that have a reduction potential, or a reduction half reaction listed below the She, right? So if we think about the She electrode, it's the conversion of hydrogen ions into hydrogen gas, right? So, right, hydrogen ion, right, acid, right? In an acid, you're going to have hydrogen ions. So if you put your metal in your acid, what you're looking at here is if you want your metal to undergo oxidation and your hydrogen ions to undergo reduction, right, then you need the metal ion to be below it, have a higher tendency to undergo oxidation in the table. So if you have a metal that's listed above the She electrode, like copper or silver or gold, right, they are not going to dissolve or react with many acids. Now, but things like zinc and iron and other metals, right, that are listed below, so if we sort of flash back here, if we see all of these metals listed below this, right, all of these metals are going to react in acid, right, whether it's aluminum or manganese or zinc or chromium or iron or nickel, right? These are going to react very nicely in acids. Metals that are up here, silver, copper, gold, right, way up here, right? Platinum, right, which isn't even on here, but it would be way up here, right? These are not going to react. Now, not all acids are quite the same. Nitric acid is special, right? And if you remember back to Chem 1, right, we saw the reaction where copper did not react with hydrochloric acid, but it did react with nitric acid, because in this case, the hydrogen isn't being reduced, but the nitrogen is being reduced. And so what we have is the reduction of nitrogen from NO3 to NO. So nitrogen here is a positive 5 oxidation state, and here it's a positive 2 oxidation state. And so we see the reduction of the nitrogen. And if we look back at our potential table and we look at the nitrate, that's a 0.96 volts. So now the metal just has to be below this instead of below the She. And so clearly copper is below it. So by having the ability with the nitrate ion for the nitrogen to undergo the reduction, now this reaction, you can get the metal to react. So this is positive 0.96 volts. Right? So now the copper is well below that, positive 0.34, and so now you get a spontaneous reaction. And if you remember, we do see that react and you create NO gas, which is a nice brown gas and so forth, right? Silver, gold, and platinum won't even react with nitric acid, but they will react with a special acid, which is a mixture of this. This is called aqua regia. And this will pretty much dissolve anything, and it'll dissolve gold and platinum, right? The mix of these two. Okay. Well, that about wraps up what I want to do with talking about standard reduction potentials now. We will be moving through this, and you'll be utilizing this table of potentials to calculate cell potentials, for all kinds of different things. Okay, let's close out this section by doing a practice problem. So we want to use our standard electrode potential table to predict whether a reaction will occur and to calculate the standard cell potential of a reaction allows us to do that. So the question says, use standard electrode potentials to calculate the standard cell potential for the following reaction. We have nickel 2+ ions reacting with manganese metal to form nickel metal and manganese 2+ ions. So in order to work this, we first got to break it down into the half reactions. So we have two half reactions, right? We have our oxidation half reaction, where manganese is undergoing oxidation. And we have our reduction half reaction, where nickel is undergoing reduction. So if we go to our potential table and we look up our oxidation, the standard reduction potential for our oxidation, so we have manganese solid goes to manganese 2+ aqueous plus 2 electrons. If we look in our table, what you should find is that that particular reaction has a reduction potential of negative 1.18 volts. So this is our standard electrode potential. So this is my oxidation. Right? So now let's do the same thing for the reduction. And this is nickel 2+ plus 2 electrons goes to nickel solid. So there's my reduction. If I look that up in the table, it has a reduction potential of negative 0.23 volts. And so now it's a matter of calculating our cell potential. So remember, our E cell equals E cathode minus E anode so that's going to equal our cathode, right? That's where reduction takes place. So negative 0.23 volts minus our anode where oxidation takes place, minus 1.18 volts. So we got an E cell minus 0.23 minus a minus or plus a positive 1.18 or equals a positive 0.95 volts as our cell potential here. So the fact that this is positive indicates a spontaneous reaction. So yes, this reaction would occur as written, that manganese would be oxidized in the presence of nickel ions in a spontaneous way, generating a potential difference of 0.95 volts. And so this is the idea of using these standard potentials to calculate cell potentials and then to tell whether they're going to occur spontaneously or not. Now, just so you know, I'm going to post a separate video with a couple of problems from our previous class where we balanced equations. That one got kind of long, so I wanted to post the problem separately. So I will be posting a separate problem one with problems from those first couple sections of the chapter.